let's consider the transformation T of V defined by multiplying the matrix A by the vector V, where A is this matrix. It should be clear then that T has to act on vectors in R2 and the image of a vector. The result that you get when you multiply a vector in R2 is also a vector in R2. This is because rows have length 2, so they have to multiply vectors of length 2. Hence, T acts on R2. And you have 2 rows. So when you multiply a matrix having 2 rows by a compatible vector, you're going to get 2 rows in the matrix, meaning the column vector that you get is going to have 2 numbers in it. The matrix reduces to this. That's very straightforward, so everybody knows how to reduce the matrix, meaning that the row space has basis, well, the row that we have here, the 1/1/2 vector. Okay, and it's just a set consisting of this one vector. So the row space will be all sums of multiples of the vectors in the basis. Since there's only one vector in the basis, the row space will consist of all multiples of this vector. Column space, indicated by the leading 1, is the first column of the original matrix, which is 4, -6. And again, column space will then consist just of multiples of this vector, since there aren't any other vectors to add multiples to. Okay. How do you picture this? Well, in R2. Okay, first of all, the row space consists of vectors that constitute the rows. Okay? The row space then is going to occur in this R2, and let's see. Really, I should have said T is a transformation vector space V to vector space W, where V is an R2 and W is an R2. So this vector space is going to be RV, and the row space, again, consists of all multiples of the vector 1/1/2. Well, the vector 1/1/2 come over 1 up 1/2, and then the multiples of that vector are just the vectors that pass through the origin that are parallel to this one. Okay, so this line is our row space. Now, V transforms to W, so W is going to be over here. The column space is in W, okay, because every column of A will appear in W. For example, this column appears in W simply because if you multiply this vector by the vector 1, 0, you get the vector 4, -6. Okay, so the columns of A will always appear in your second space, the space onto which you're mapping. So the vector here is 4, -6. So, well, that's going to be a little bigger vector. If we use the same scale in both spaces, and that's okay. We could use different scales if we wanted to, but this will be the vector 4, -6, and your column space consists of all multiples of this vector. So column space is represented by this line. Now, more properly, the column space is represented by a vector from the origin to any point on this line. So every point on this line, if you take a vector from the origin to that point, you get a member of the column space. Okay, and similarly with the row space. Vector from the origin to every point of this gives you one of the vectors in the row space, and if you do that for all the points in this line, you get the whole row space. Just as if you do the same thing for all the vectors defined by this line, you get the entire column space. Okay? Well, now there's another really important space, and that's the null space. which is also called the kernel of the transformation. In the null space is a set of vectors x such that ax is equal to the 0 vector. Well, this is equivalent to saying that 4x1 plus 2x2 equals 0, and negative 6x1 minus 3x2 equals 0, so that x2 equals negative 2 times x1. Now, that's going to be every point, every vector x for which the coordinates x1 and x2 satisfy this is a solution. Well, let's let x1 be the free variable. I'll say if x1 equals t, then x2 equals 2t. So we have the set of points t, 2t. And that's 2 times the vector 1, 2. T times the vector 1, 2. Now, what's that mean? Well, the null space is a set of vectors that A acts on and takes to 0. If A acts on the vector, it's in the vector space V. The 0, of course, would be over here. Okay? Because that's the result of the product. Well, the vector 1, 2, let's see. Here's a vector. Uh-oh, wait a minute now. It's that would be negative 2t. Then we'd have a negative here and a negative here. Okay? So it's really the vector 1, negative 2. Excuse me, 1, negative 2. That might be about here. Okay? This is the basis for the null space, because every vector in the null space is a multiple of this vector, so that, don't really have a good place to write it, but the basis of the null space, don't want to clutter up the picture, I was tempted to write it, okay, is this vector, the vector 1, negative 2. We'll write it basis of the null space. Meaning that the null space can be represented by this line in the sense of the other lines. Every point on the line is a vector in the null space because every point on the line is a multiple of this vector. Or every point on the line is identified with a multiple of this vector. Okay? Okay, well, that's pretty good. But I guess I can notice one thing. The slope of this line, okay, well here's your null space. It's all the vectors defined by this line. Here's your row space. All the vectors defined by this line. The slope of this line is 2. 1/2. And the slope of this line is negative 2. Well, that means the lines are perpendicular because this slope is a negative reciprocal of this one. Okay? Now, all the vectors in your null space, every vector that's defined by a point on this null space maps to the 0 here, which means I've labeled everything kind of unfortunately, but the whole null space, take the whole null space, it maps to the 0 vector. Now, the other thing is, as we just seen, these lines are perpendicular, so that the null space is perpendicular to the row space. Okay? And that's always going to be the case. You can prove that it always is. Okay? Not just for 2 by 2 matrices, for any matrix, and it's not that hard to prove. Okay, I'm going to write down a statement. I don't want to, it's going to be long enough that I want to just write it down and then go to the next video.